In the last video, I added the WindForce, Gust and School features to the plugin, and although this creates a self-contained plugin, there are some potential performance issues. In this case, the plugin is simple, but as the complexity grows, there is a risk of buffer underrun, particularly on low-powered mobile platforms. In this video, I will explain how to take advantage of modern CPU architecture and how to avoid some of the potential pitfalls. And in the following videos, we will implement these features in the wind effect. So first, some background information. This is often how we think a CPU accesses RAM. The CPU reads and writes the data to RAM as required as the CPU cycles through the instructions. However, this model has changed many years ago as clock speeds haven't increased greatly, so other techniques have been used to make the processors get faster. Cache memory, for example, multi-cores and prediction circuits. In fact, probably only 10% of the silicon in a modern CPU is now actually doing the calculating. The rest is just feeding the processor with data more efficiently. This is the memory model of a typical modern multi-core processor. RAM access is much slower than the CPU processing ability, so data is passed through faster cache memory, level 1 being the fastest but smallest, and level 3 being the biggest but slowest. The CPU cores will directly access the fast level 1 cache, which is split by instructions and data. Dedicated memory management circuits will pass data through the cache memory to feed the CPU cores. It will try to predict what's required so the data is pre-fetched where possible, so the processor is not kept waiting. The data is fetched in chunks known as cache lines, which are typically 64 bytes long, although Apple Silicon M1 is 128 bytes. So say your program needs a 4-byte integer. The memory management system will load these bytes into level 1, but also it will load the adjacent 60 bytes in memory, just in case. So memory structures in your program can take advantage of this by keeping data you use in the same program segment in contiguous memory. And what you'll see me do is creating structs, as they're very useful for this. Next, we will look at how the CPU executes instructions. Modern CPUs don't execute one instruction at a time, as they have a pipeline of parallel instructions. The typical pipeline length is 14 to 20 instructions depending on the CPU. The instructions are passed through various parts of the CPU with each clock cycle to maximize the use of each circuit within the CPU. Initially there's a little latency as the pipeline is filled, but then the CPU will give the impression that each potentially complex instruction is only taking one clock cycle. This makes the CPU on average much faster, but there are potential pitfalls that will cause the CPU to stall. First, we have data hazards. Data may be needed by future instructions before it's written from the registers of a previous instruction, which can cause delays. Also branches. Branches are very common part of programming. If statements, switch statements, loops, etc. The result of the branch is only known at runtime, so the instructions to run after a branch is not certain. Branch prediction circuitry helps, but there will always be branch prediction misses. When this happens, the CPU pipeline must be flushed, so all the work in progress after the miss is wasted, and the registers must be reset. This inevitably creates a penalty, which normally is not noticeable, but for hard real-time applications like audio, this is very undesirable, as we need a predictable processing rate. Now we can apply this knowledge to our Juice plugin. We can ignore the GUI thread, and we will concentrate on the audio thread. The audio thread has three main components: the constructor, which is called when the application is first executed; prepare to play, which is executed by Unity or whatever host we have to set up the DSP code; and then process block, which is called every time more audio is required. This is called the audio callback. This is the hot loop and is where we need to concentrate our efforts. The audio callback will receive a reference to the audio buffer in Unity, and this buffer must be filled within the buffer time length, which is basically the samples per block divided by sample rate. This creates a hard real-time system. Neither the hardware, for example the pipeline, nor the programming language, C++, are actually designed for hard real-time systems. And later I'll show you some very innocent C++ code which can work against us. Finally, the audio thread is always high priority, so should be executed first. But always be aware not to call lower priority functions from inside the audio thread. So for audio programming, we can define what we mean by performant. We are looking to create a consistent or known number of processor cycles per process block wherever possible. We look to reduce latency by creating smaller block sizes, so we actually have less time to fill the buffer. Our objective is to create the least worst number of CPU cycles per block. It is the worst case that will cause that click. Most programming looks at amortized performance, so will sacrifice the occasional delay for best average performance, and this is actually contrary to what we need. However, there is a compromise. As for mobile platforms, there is a power consumption to be considered. The code you write isn't necessarily the code that's run. The compiler and CPU can optimize your code, so measurements are always important. Xcode has built-in profiling tools called instruments, which allow performance to be measured. Similarly, Visual Studio has tools. But beware, the most valuable information is the time spent in the process block, but this is virtually impossible to extract reliably. The profiling tools themselves can add overhead, but worst of all is the operating system. The operating system, particularly Mac operating system, will run the CPU at the slowest speed possible to save power. So good code and bad code can give unexpected results, as the operating system can decide to run the CPU at higher clock speeds for the bad code. There is a programming rule that says don't optimize prematurely. However, in this case, we know where to optimize, so to some extent we can break this rule. To create high-performance code in the process block, we need firstly to write efficient algorithms that are sufficient for the purpose. An example is calculation of sign, which is often needed in audio. Don't just use the library sign function, as processor cycles are wasted for unnecessary precision. There are sign approximation algorithms which are often accurate enough. I used to use lookup tables, but I found that these are often less efficient, probably due to cache misses, as the lookup is not strictly sequential. Efficient CPU usage is achieved by avoiding potential branch mispredicts and using compound calculations, but make sure these are not too complex. Use structs to create contiguous memory, where a set of variables are used close together to take advantage of cache lines. Also consider data alignment. Data alignment is a word, 64 bits or 4 bytes, so align data in 64-bit chunks. So if you have a 2-byte piece of data, try and put it next to another 2-byte piece of data so that the data actually aligns nicely. Only do what you need to in the process block. This is the issue with the last video. The plugin can be simplified to accept just wind speed, and the wind force and gusts can be moved to the game thread, where branches are less of a problem, as the game thread is not hard real time and can be flexed if it needs to. Control signals should be in the game thread and smoothed in the audio thread if necessary, using simple low-pass filters or interpolation. And then beware of library functions. You must understand what impact they have. Even some of the juice library functions must be used carefully. Finally, it's always worth profiling your code to make sure there are no surprises. So the rules. We've already covered predictable code. And next we have runtime safe functions. We're in a multi-thread environment, so it can give rise to locks, where the audio thread could be locked while waiting for something to happen on another thread. This can be disastrous, as the other thread could be low priority, so locks should be avoided at all costs. Waits should be minimized, where the audio thread may have to wait a few cycles to access data that's actually being used by another thread. This is unavoidable, as there are always times when data is being passed between threads. In our Unity plugin, this is invisible to us, but you should be aware that data is being passed from the game thread to the audio thread, and this can cause waits. Whatever you do, don't allocate or deallocate memory in the process blocks. A good example is don't resize vectors. Always allocate on construction and deallocate on destruction. Allocation and deallocation always creates locks. Don't read keyboards, mice, networks, or anything else like that on the audio thread, and no operating system calls, as these will be lower priority and may cause locks. If you're calling functions, always understand how they work. Atomics use CPU hardware instructions to read and write data, and this is how data is passed between threads reliably. They guarantee a read or write is done in one cycle, so there's no torn data where the data is changed during the read process. They are lock-free but not wait-free. They are needed in they're not needed in our example, but they are used extensively in JUICE. Then there are denormals. These are float values that are less than the smallest float value. The exponent bit of the float is 0, but the fraction is non-zero. When you're using filters or feedback where the output tends towards 0, always consider denormals. JUICE has snap to 0 function to deal with this, but sometimes you have to code this yourself. The CPU will attempt to process a denormal number, but the number of processing cycles is huge, say 100 times what you would expect, so can create nasty bugs. In terms of programming style, we should always seek to pre-calculate variables rather than calculate them in the process block. Decrementing a loop is slightly less expensive than incrementing a loop, but it's not massively important. Reuse of temporary variables rather than declaring multiple variables is useful to do. Always try to traverse arrays sequentially to improve the cache. Order instructions carefully so there are fewer potential data hazards, and think about data dependency. A good example is a plus b star or multiplied by a minus b can't be executed in one cycle. There's a data dependency there. Although in a loop this may work okay. Logical operators can cause unexpected branches, and this is quite an innocent part of C++. So beware of short-circuit logical operators such as and the or, the bar, or functions. This is actually due to the C++ standard, which says if the left side determines the result, then don't evaluate the right side. That creates a branch. I.e., the left side of an and evaluates to false, then the result must be false, and so the code will branch, so the right-hand side is not executed. Now this, on average, saves time, but is not particularly helpful to us. If you want to see this in action in the assembly language, you'll see a conditional move statement, CMOV, which mitigates the branch problem. What this does is actually moves data rather than creates a branch. So if you see this in the object code, then actually that's a good thing. So finally, branchless code. This will increase average processing time, as you will actually do more calculation, but avoids branching, which may stall the CPU. So looking at branchless code in a little bit more detail, an if statement can be converted to branchless code by using a Boolean. For example, if A, then multiply the result by X, else multiply by Y, becomes Boolean A times X times result, plus not A times Y times result. Simple if statements will probably be optimized this by the compiler anyhow, but not always. There is always a branch at the end of the loop, so you may want to unroll a loop if it's short. Although sometimes the compiler may do this, it may even vectorize it, where it calculates up to 4 iterations simultaneously, although in my experience compilers are not great at doing this yet. The ternary operator is also useful, as it will be more reliably branchless, but simple if statements will be optimized in this way anyhow. Although in our example the branches happen only once per block, the effect is not too severe. However, I want to show you that we can write this plugin more effectively using the techniques we mentioned in the video. So in the next video we'll rewrite the plugin and remove the control signals from the plugin. And we basically just plug in wind speed into the plugin. We can avoid branches in the code, improve the memory management of the plugin, and we'll add a few more features. And then in the following video, I'll show you how to write the C# script to bring back all of the wind force and gusts and various other bits and pieces, but doing this within the C# script within the game thread. So I hope to see you next time. I hope you enjoyed this video. Thanks.